Okay, let's move on to the next one, which is QoS. I love QoS. Everybody hates it, but I love it. And the reason why is because it's a very boring topic when it works, but when it doesn't work, that's when you want to read about it. And here in Wi-Fi, we have this issue where we have QoS everywhere on the Cisco network, and you know that, right? We have application visibility and control on the controllers, on the switches, on the routers. We have remarking. We can do all sorts of things. The only thing we couldn't do is influence those devices. So we could not control QoS between here and the access point. Because basically, we cannot control the client, right? It does what it wants. It can send whenever it wants. So we say we have end-to-end QoS, but QoS is as good as your weakest link. And we have no control on that link from the client to the access point. So when we started working with Apple, we say, well, that's a place where we can improve things in enterprise networks. So what we did with them is to say, okay, look, first we're going to talk about QoS and practices of QoS. So we spent a lot of time talking RFC 4594. You know that RFC, right? Everybody reads it every evening. So you know that's the RFC that says these are the different types of traffic we can expect in the network. And this is the type of treatment we need for this traffic. There are recommendations from the IETF. So we follow these recommendations mostly at Cisco. So we talk with Apple and we say, okay, if we were to implement the RFC for all the traffic we have from iOS devices, what traffic would get what type of marking? And then based on this DSCP marking, what layer 2 wireless marking should we have? Because we have only 4 marking we can play with at QoS for Wi-Fi. So we had that done, and that's a great step ahead. And then also we said, we're going to allow you, if you are managing a fleet of devices, to create a profile. And that profile is going to be sent to the device, and that profile is going to determine what we call a whitelist. That whitelist is going to say which applications in this device, in this network, are business relevant. Those applications will have the right to mark QoS. The others, outside of the whitelist, will be just best efforts. So the way you create this list is very simple. You can create it on the MacBook if you want to. If you have an MDM solution, you can also create that MDM solution profile and push it down to the device. And it looks like this. This is the Apple configurator on the laptop. This is the Meraki System Manager MDM. And you see when you configure profiles, and in iOS you had profiles since iOS 4 or 5, it's been a very long time. But what is new in iOS 10 is that when you go to the SSID, the wireless, the Wi-Fi, and when you configure the SSID profile, before you could configure the security settings, etc. Now at the bottom there is also Fast Lane QoS Marking. And here you can just click there and start typing application names like Cisco Spark or anything else, and it's going to pull from the App Store the name of the applications, and it's going to save them for that SSID in that whitelist. Then you push that whitelist down to the client, and now when your client shows up in that network, it's going to do the same thing as before. It's going to say, if it's not a Cisco network, I can apply my profile, but I'm not going to care about the QoS profile. So there is no differentiation between traffic. But if it's a Cisco network, then we still have this handshake system, so we recognize each other. And then if it's a Cisco network, it's going to look at if there is a profile for that SSID in the device. And if there is a profile, it's going to activate it. And again, only the applications in that profile will have the right to mark QoS. The others are going to be best effort. Where is that useful? Yeah, there's so many cases because it's on a per SSID basis. So think about it. Think, say, you are in a school and you're a teacher and you are teaching your kids about minerals, for example. And of course, minerals, how do you teach kids about minerals? You play Minecraft, right? Do you guys play Minecraft? Well, that's the way to teach, right? And it's because it's educational, right? So in that environment, strangely enough, Minecraft is a business relevant application. It's relevant to what they do, right? So you can put Minecraft for the school SSID, you can put Minecraft in the whitelist, and Minecraft will have QoS out of these devices. Now, if you're using, say, Spark and you don't use Viber for voice, Viber is just for personal calls, then you can put outside of the whitelist Viber, which means that if you place a Viber call, it's best effort, so we'll send a packet if we can. But if there is a congestion time and we have to choose between real-time interactive Minecraft, business relevant, and Viber, not business relevant, we're going to send more frames of the Minecraft business relevant packets than of the Viber. So again, we're not blacklisting Viber, right? We're just saying your best effort. If we have the space, we'll send you. But if we have to arbitrate, we're going to use arbitration to prioritize business relevant applications. All right, that's in the school. Now on your same phone, you move back to Cisco. And last time I checked with Cisco IT, Minecraft was not business relevant at Cisco. We're working on that, but today it's not business relevant, which means that it's not in the whitelist. Therefore, if I play Minecraft at the office until I get caught, it's going to be best effort, right? And maybe Viber for some reason is business relevant and it could be in a whitelist and they get QoS marking. So 2 things to keep in mind. This is based on SSID, right? So you can have as many lists as you have SSID profiles. So that's very powerful and very flexible. Say you are in a dormitory, you may have Netflix allowed in a dorm in a university. Then you move to the classroom, Netflix is not in the whitelist anymore because here you're supposed to work. So it's very flexible. The second thing is to keep in mind is that we are not sending QoS marking, right? We're just saying, yes, you can mark, no, you cannot mark. So you're going to be best effort. This is super key, and if you understand QoS, it's obvious, but we have so many customers, you wouldn't believe it, that come to us and say, well, this is voice, right? I say, yeah, it's voice. And you say best effort, yeah. But, it's still voice, so what if I want to still give priority to that thing? So instead of giving 46, which is, EF voice, can you give me something that is not best effort, but still voice-ish like, I don't know, 43 and a half, or maybe 42, give me a price, 40, and we say, no, all right, this is not the way QoS works, right? That's why we have RFC 4594 that says, you have classes of traffic. If your class is voice, you have 2 states. I care, you mark voice. I don't care, you don't mark it. And then best effort will do the thing, it will send if it can, but if it cannot, it's not going to put it in another queue because that other queue is used by something else, video or something. So that's very important to clarify. Also, we have classes of traffic, and each of them is set for a certain type of traffic. Another question we get is, so how does that application get QoS? What is the marking? Where does it come from? And the answer is, we worked a lot with Apple to clarify for the developer world what kind of calls can be made at the application level now to benefit from this QoS. In iOS 9, there were, I think, 4 QoS queues. Now in iOS 10, they have 9 QoS calls that can be made so that you can have voice, video, OEM, there are a lot of variations of possible calls. So it's a developer's job to educate themselves and make the right call.
So the developer has to do the right stuff to mark the traffic properly.
Yep, the question is, the comment is,
yes.
The developer has to do the right thing, and the answer is yes. And
finally someone got it.
And it's funny because when we said that, most people reacted saying, but what if they mark everything DSCP46? Like they do a BitTorrent application and they mark it voice. Then we say, dude, it's not going to do anything good for them because the DSCP46 queue here is built on the expectation that these are going to be small packets at 20 millisecond interval. If you start putting large frames, you're going to just kill your buffer. So the experience is not going to be any better just because you cheat. And by the way, we'll report you to the App Store and you'll be kicked out of there. But until then, the experience is going to be bad. So educate yourself, do the right thing. Your application will be better. And it's, it requires education. I was talking a few weeks ago with healthcare application developers, and they are making an application that allows you to remote control from an iPad a blade for the operation room. And they were saying, so what is the marking for that packet that goes down to the blade? Remember, you're sleeping and something is cutting into you. And we say, what kind of QoS do you want to put for that packet that says stop cutting, for example, or cut higher? And we're saying, well, the RFC is not clear on that, but basically anything else can stop, right? Because if that's wrong, that's a catastrophe. So there is a classification that needs to be exchanged between the developers and people who understand QoS, saying, really, this is going to be AV, that's going to be very high QoS, because although it is not supposed to be in those categories described by the IETF, they have no description of that type of traffic, and in the priority level of everything in that environment at that time, this is the most critical packet. So the marking needs to be exchanged with the developers. All right, so the result is that when you are on Fast Lane network, your application is in the whitelist. For example, you'll get voice, and on the way back and video, you will get the video upstream. Now, if you are non-whitelisted, you're the best effort guy, then the same traffic will get 0, 0 for voice and video. Same network, we just turn Fast Lane off and you're out of the whitelist. Now, what about non-Fast Lane network? I don't know, I don't do non-Fast Lane networks. But if you do ever, so you will still have the marking that they used to have before, where you have the layer 2 QoS, but you don't have layer 3 QoS. And the reasoning here is to say, if it's not an enterprise environment, I do not want to mark DHCP, because you will get into your home router and that packet may not be understood. So in a home environment, that doesn't make sense. So the expectation is that if you're non-Fast Lane, we do not know if you are a home environment or something else. So the expectation is to give you priority in the air, but beyond the air, we don't do it because we don't know what's there. A few more things on this. We had actually few more features that we developed together. We said when people configure QoS on our controllers, very often they have a hard time understanding what should be configured and how it works. And there are best practices guides that we publish all the time, and people sometimes read them. There are long documents and it's easy to lose track. So we have in the controller some features which are best practices page, where we can go there and check if you're following the best practices. But we also thought, as we configure Fast Lane on the controller, and I'll show you how it's configured, then you're probably caring about QoS. So we are going to do you a favor, and when you enable Fast Lane, we're going to configure a few things for you, which are going to be the best practices on the controller. So there are quite a few ones, so here it's more for your reference than anything else. I will show you some screens. But here again, we have the same question, and we say, how do we know that Fast Lane is actually improving the quality of experience? Because it's nice to develop stuff in the lab, but if it doesn't translate in real gain in the real world, we're wasting our time. So what we did here is that we did a roaming experience where we had a voice call, and we liked voice calls because it's one packet every 20 milliseconds, so we have a good timer of packets being sent out. Then we load the cell to 70 or 80% channel utilization, which is pretty high. There is not much can be done at that level. And then we place a call, and what you see here is measured in the air outside of the phone. What is the average time, the average interval between one packet out and the next packet out? So the green line here is my 20 millisecond line. And you see that mostly with Fast Lane, we are about 20 milliseconds. Sometimes we get delayed, right? Which means that the next packet is sent immediately after if we can. So that's why you see those jumps here. And because of the congestion, sometimes we get delayed badly, but we averagely never go beyond 100 milliseconds, which is again the threshold where you start hearing it. Now I turn off Fast Lane and I go here. Now my average, so my green line is still at the bottom here. My average is about here, which is about 40 milliseconds. It doesn't look much on a screen like here because you say, yeah, it's 20 milliseconds more, big deal, it's just 20 milliseconds. But you have to keep in mind that this is a real-time flow, right? So that means that you're sending one packet every 20 milliseconds. And you cannot buffer them for 10 minutes, like say, Grandma, I'll tell you in 10 minutes because there is congestion. It has to be real time, which makes that your phone, if it doesn't send the packet within a certain interval, and typically it's 30 milliseconds, depending on the application, but if it doesn't send the packet within that time, it's going to say, well, I have to maintain the impression of real time at all costs. So I'm going to drop that packet and send the next one instead. Which means that here, if your average time is 40 milliseconds, that means that you're dropping every other packet. You send one, drop the next one, too late. Send the next one, drop the next one, too late. So when you are on a call, you can't really tell that somebody's speaking. You hear sort of metallic, you have that before long ago, right, in the cellular times. You just don't understand what people are saying. And sometimes the interval is even higher. You have some times where you get even dropping the call because it's too high. So just turning on Fast Lane, because you bring the priority level from not much to priority 6, it really makes a big difference in the prioritization of the voice. I know it's not magic, right? It's just basic QoS as it was implemented in 802.11e and in the IETF protocols, but implementing it really makes a difference in congested environments. I do not wish to anyone to have 80% utilization of your cell. That's very high, but it happens and you have congestion at some times. What is key to remember also is that when congestion happens, the effect of congestion lasts, which means that if my call is bad, I'm losing packets. Even if my condition get back better, it will take a while for this guy to realize that congestion is gone for real. It's not going to come back, and it's going to reinflate its transmission. So a few seconds of congestion can mess up your call for 20, 30 seconds easy. So those waves of traffic are enough to destroy the communication. So Fast Lane is not on by default on the controllers because we don't know if you have iOS devices. We don't know if you care about QoS if you have iOS devices. That's something you turn on and it says, oh, I'm going to do all these things for you. And it's going to configure all these things, configure all these profiles, the best practices at the same time. What I'm very proud of is this one, EDCA. So what this is when you use QoS in wireless, the access point can send transmit opportunity messages. So what that means is that in 2005, when they implemented QoS for voice, they said, before, if you have to send a frame, you pick up a number, count down from that number, and when you get to 0, you send your frame. Next frame to send, okay, pick up a new number. And then they say, well, wait, if it's voice, that is stupid. Because your voice packets, you have plenty of those. They're super small and you have plenty of those. So you're going to count down every 20 milliseconds, doesn't make sense. So what we're going to do is to send transmit opportunities to the cell saying, if you are a voice packet, you're in the voice queue and you get down to 0, if you have more than one packet to send, go on. Don't pick up a new number, just burst, 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 burst. And you can burst for up to, and you give a number, and that's the transmit opportunity. Typically, it's 1.5 milliseconds for voice, 3 for video, real-time video, because they are larger packets, but then it's 0 for best effort, and it's 0 for background. The idea is to say, hey, for best effort and background, you have to count down for every packet. That was super smart in 2005. But then we had 11N and 802.11ac, and everybody has those, right? You have 11N, 11ac. And 11N, 11ac have what we call blocks, where you can basically group frames together, and you send a big train of frame. And those are sent at best effort. And the problem is that technically, it's one frame, but it's a big one. So the result is that with these transmit opportunities we had before, you say, oh, if your voice, you have to send to up to 1.5 milliseconds max. Or if your best effort, as long as you send only one, you're good. And then you can send a gigantic frame through. So the result is that your voice and your video now have lower priority or access to the medium than best effort or background. So of course, the IEEE realized that, and in the new revision of the protocol that actually came out in January, they have new values. So they set maximums for all the queues, and those maximums depend, of course, on if you are doing voice, video, 11N, 11AC, 11G, 11A. So depending on the protocol, of course, the speed is going to be different, and therefore the prioritization is going to be different. So we have that information since last year, and since last summer, we have those new recommendations from the IEEE in our profile. So when you activate Fast Lane, we turn on these new optimized transmit opportunity mode automatically. Okay, so that's one of the few things we do. We also trust the SCP upstream. We've been working a lot on QoS in wireless for the last 2 years, and all these best practices we've designed, we implement them into the network. So what does that do for us? To me, that it's super exciting. I know I couldn't sleep when we had this feature the first time, because we said, for the first time in the history of 802.11, we have end-to-end, real end-to-end QoS, not from the API and up and then back down, all the way from the client, all the way to the end of the world, and then all the way back to that client. We have that now. And that's, to me, a huge win, because if you know QoS, you know that if there is one link that's missing, well, that's a problem. You don't have QoS. This guy is going to kill your throughput possibilities. And we had that for wireless, and we used to say, can't do anything, clients can't control. And now we say, no, we cannot control, but we can talk, and we can tell it, this is what matters in this network. So that is, to me, very exciting.